All right, so prufer sequences, it's literally just you build a finite sequence, assuming it's a finite tree. I guess you could totally do this with an infinite tree too, but we're not going to deal with infinite trees if possible in this class. Okay, so you've got some tree. The number of vertices in that tree is n, whatever the number of vertices is, and the actual sequence that you build is going to be 2 numbers fewer than the number of vertices you have, and that's because when you start with your tree and you build your prufer sequence, the very last thing that you get to is a single edge with 2 vertices as the endpoints, and so for those guys, since it always ends that way, you essentially truncate your sequence too short. Okay. The things that go in the sequence are specifically your internal vertices, and what this is doing is it's tracking how the structure of the tree is built, working from the leaves in. Okay. Now, for these prufer sequences, there's nothing here that requires you to have a rooted tree, and in fact, if you do have a rooted tree, you would actually be ignoring the root. Realistically, what would happen with the root is it would be one of the end numbers that would come up in your sequence right here. Okay. So last time we looked at an example, and the example we had was just a relatively unadventurous tree. It reminds me totally of a guy sitting and waving his hand. Okay, and the numbers here on the vertices were picked 1 through 8. One of the things that's standard when you encode your tree with a prufer sequence is you typically have your vertices labeled numbers, specifically the integers 1 through, and the highest number you have is the total number of vertices you have. So for this tree, we had 8 vertices, and we labeled them 1 through 8. And the way that I've presented the algorithm for getting this particular prufer sequence really does depend on the fact that you're going to be having the numbers 1 through the number of vertices you have. This can be adjusted, but you would actually have to adjust some of the strategies here. Okay. So what we said we did is we had 2 things that we were dealing with when we encoded the tree. We had the actual sequence, which are tagged by these S in the subscripts, and then we had the leaves that gave you the sequence terms, and we labeled these with a lowercase l. I do a script L just so it's obvious that it's an L and not like a 1. Okay. And I did match the subscripts so you know what stage or step we're at. Okay. So you look at your tree, you pick the smallest leaf that's currently in the tree, and when we say smallest, that would be in terms of numbers, numerically the smallest. If you used alphabet letters, this would be the one that's first in the alphabet, would be the conversion. So notice you can convert to other types of vertices. Now, the thing that actually goes into the sequence would be the vertex adjacent to that leaf. And remember, all of your leaves are degree 1, so there is no option here in terms of who are you going to put for this S1, this first sequence term. This vertex 1 is only adjacent to 1 vertex, so you're forced. There's only 1 possibility here for this 6. Okay? And then what do? You remove the leaf that you just used and repeat the process until you get all the way down. And what we did is we actually did snapshots of what happens when you remove the leaf. So the next one, we removed the leaf that was at 4. Next one, we removed this leaf at 5. Next one, we removed the leaf at 2. The next one, we removed this leaf at, well, we had 6, 7, or 8, so we removed the leaf at 6. We removed the leaf at 7. And what got scooched to the side was our very last snapshot. And our very last snapshot of us very much desiccating this tree was getting 1 edge and 2 vertices, and this is when you stop. Okay? So what we did is we then looked at all of the S with the subscripts, and those guys were our sequences. So the prufer sequence that corresponded to our given tree that was back up there looking like a guy sitting down and waving his hand was the number 6, 2, 2, 3, 3, 3. Okay. So that's where we ended. We started looking at, all right, well, how would we, if we were given the prufer sequence, recover the tree? And we got like partway through, and then we totally ran out of time. I shouldn't have even started it. We were so close to time. So let's now go backwards. So this time we'll look at this. I'll actually go ahead and pull this exact example right here. Why? Because we go and we'll go and build it back to the original tree, and we can match to see, did we really get that originally starting tree? Okay. So that is a good question. So the question that came in was talking about what happens if the labels on the tree were different. So if we come back up here, if these labels on the trees were different, you would actually, yes, you would get a different prufer sequence, because the prufer sequence is built off of who is your smallest leaf. So if you had gone in here and grabbed, say, I don't know, how about 3 and 1 and switched them out, yes, you would get a different sequence, but you would still get an isomorphic tree, correct? The only thing that would change is you get the same tree, well, isomorphic because maybe instead of having this guy be at 90 degrees, you actually made that edge just extend out like a path, but the labels would be scrambled in that same way that you had originally scrambled them. All right, so if we go ahead and look at this guy, so again, we took the exact same prufer sequence that we got before. So here's the starting point. First thing that you would do, and let me actually make this as a method, sort of giving you an algorithm, if you will. First thing that you would do is you will need to figure out how many vertices you're going to have in the tree you're about to build. If you don't know how many vertices you're going to have, issues ensue, okay? So the number of vertices of your tree is always something plus 2. Well, that something is the number of terms in your sequence. So for our sequence, how many terms did we end up getting? We ended up getting 6. So total number of vertices should be 8. Okay? So this right here, this plus 2, that part you always do, and that's because the way the prufer sequence is built is the last 2 vertices don't really get included into the prufer sequence. Okay? Now, once you have your prufer sequence, the second thing you do is you set up. Now, in terms of the setup, what am I going to do? I'm going to take the fact that we have 6 terms in our prufer sequence and do that same leaf sequence pattern that we had before. Now, I don't know, let me make this go away so we can see this bigger. I don't know what the leaf is, but I do know what the first sequence term is. It's 6. And we then repeat the process for as many sequence terms as we have. Again, I don't know what that second leaf is yet, but I do know the second term is 2. I don't know what the third leaf was associated to the third sequence term, but I do know that third sequence term was 2, and the last 3 sequence terms are 3, so I'll do the same thing but with 3s. So L4, we don't know. S4 is 3. L5, we don't know, but S5 is 3. And the last one is 6. So L6, don't know, but S6, we know is 3. Okay? And I would recommend, you don't have to do it this way. I would recommend, though, mapping this part out, put in all the stuff you know right now, and then we'll go back in and fill in the leaves. Once we have the leaves, we'll be able to build the tree. And we'll actually fill in the leaves and build the tree at the same time, is the plan. Okay? So we'll set up the chart. And we're also going to set up a list of potential vertices. And this is where I said, remember, we're going to assume that our vertices are labeled 1 through the number of vertices we have. So for us, over here to the side, our list of potential vertices is going to be the numbers 1, 2, 3. Where do we stop? When we get up to 8, which we said was the number of vertices we have. Don't overthink this. 7, 8. Now, aside. I realize now I don't have a good place for an aside, so let me move that thing we just drew to a little bit further on down, because this aside is why we're about to do what we're about to do. Okay? So, aside. In your prufer sequence, so the prufer, not going to lie, I often call it a prufer code. So I'm trying very hard not to do that today. Your prufer sequence only lists out your non-leaf vertices. In other words, your internal vertices. Which means, in this example, our leaves of the graph, once we draw it out, are all the guys not listed in this sequence. So notice terms listed in the sequence are 6, 2, and 3. That means in the graph we're about to build, the leaves are supposed to be 1, 4, 5, 7, and 8. And those are the proper leaves of the graph. Those are the actual leaves of the graph. But remember what happened when we built the actual prufer sequence. When we dealt with one leaf and got the term of the prufer sequence associated with that one leaf, what did we do? We removed the leaf. So previous guys down here that are still called leaves are still labeled with an L. Aren't always real leaves of the graph. Maybe they're leaves of the graph after we remove some edges. So certain internal vertices. So in terms of the numbers we'll put in here for the L's, they will be some of these guys, but not necessarily all of them, okay? But there's our aside. And then the third step we're going to do is actually figure out our leaves and build our graph. Okay? So we'll move this up. So here's how you structure this. You're always going to look at the interplay between your potential vertices, or your vertices that you're actually going to use to build the graph, and filling in this chart. Now, remember what we did when we were filling in the chart, and I'm going to fill in this chart top to bottom. So we're going to mimic exactly what we did to build the prufer sequence originally. What did we do for the first leaf? For the first leaf, we looked for the smallest number on the smallest actual leaf. So I went ahead earlier and underlined these guys. That was strategic. We're totally going to use these underlines. Okay? So these numbers that are underlined, these are legitimately not leaves right now. So if we're looking for the smallest leaf in the graph, putting an arrow in the direction we want to look, we'll look 1 through 8, but ignore the 2, the 3, and the 6, which we know are not leaves. Okay? So who's our smallest leaf in that list? While you're doing that, I'm going to change back to black writing. Exactly. You find the smallest number that's not underlined, so in our case, that would be 1. Now, once you put in that number 1 as L1 up here, we can do two things. The first thing we can do is actually draw in an edge. Remember, this leaf was connected to the adjacent vertex that was listed in the prufer sequence. So 1 and 6 are going to be attached to each other. So here's 1, here's 6. Okay? So that's step 1. The other thing you can do is, it's a leaf. What did we do when we moved on? We removed that leaf from the graph. So we're going to remove this leaf from the potential list of vertices, so that L gets removed. Now, look at the 6. Is the 6 used anywhere else as an internal vertex in the future? And then the answer is no. So as soon as you use this 6 the very last time, we are going to remove it from the list of vertices we're not allowed to pick as leaves. It's now a potential second stage leaf, if you will. In other words, a leaf of the adjusted graph after you would have removed edges. Now, let me write down what we just did. So this guy right here is the smallest leaf that we're allowed to pick right now. So anybody who's not scratched off and doesn't have an underline in terms of this notation. Specifically, it's somebody who is not in our set of the prufer sequences. Okay. Now this second one is given, so you don't have to do anything with this one. And then when we look to go down to step 2, we're going to remove S1. Well, actually, we did two things. So remove L1 from list. Once it's listed as an L with a subscript, it'll never be used again. And we're also going to make S1 a potential leaf. Wow. Forgot the A. Pretend that microscopic thing is an A. That is not a good enough A. Just a second. We'll erase. Okay. So that's the idea in terms of scratch work. Now, let's do step 2. So step 2, now what have we done? 2 and 3 are still internal vertices. They're still in play because they're still being used in the prufer sequence. 6 now is fair game. But we still have the other proper leaves of 4, 5, 7, and 8. So again, you look at the smallest number in the list that's not currently being used in the sequence. And yes, exactly, it would be 4. So we'll go ahead and put a 4 in here. Now, putting it into the graph, this tells you that 4 and 2 are adjacent vertices, so we'll attach 4 and 2 together. Neither the vertex 4 or 2 are already in the graph, so we're going to have to build a disconnected graph. Don't forget the edges, I almost did. This does happen if you're working through the algorithm top to bottom, is you will get picked up pieces here that don't connect together, and that's totally okay. It happens. Okay? Now let's go ahead and adjust our list of potential vertices. We just used 4. Now, last time we scratched off the 6 to put it back in the list of potential vertices we're allowed to use. Here, when we use 2, 2 is still being used, so 2 will stay in our list of vertices that you don't get to use yet. So then we move down here to step 3, and I guess is what L3 would be. Yep. So L3 would be 5, and that's if we're looking at the list, it's the smallest number in this list that we're currently allowed to use. We're allowed to use anything that doesn't have an underline. So our options were 5, were 6, were 7, or 8. So 5 was the smallest, so we picked 5. Now, moving down to the actual picture of the tree we're trying to draw, what happens? Well, 5 is connected to 2, so we'll go ahead and connect 5 to 2. Okay? We'll also need to go ahead and scratch 5 off of our list of potential vertices, because once he's used, you don't get to use him again. Okay. Now, always do a quick double check of your sequence terms. The term used here in the sequence is 2. Do we use 2 later on for our sequence? We don't, so if this is the last time that we use our sequence number 2, that means we're going to adjust the notation on the 2 as well. Am I still orange? Nope. Which is we're going to cross off the restriction that says you're not allowed to use 2. So at this point, we are now allowed to use 2 as one of our potential candidates for L insert appropriate subscript as needed. Okay? Which means when we come down here to step 4, any guesses what L4 gets to be? Exactly. So L4 gets to be 2 now, and as soon as we put in that 2, we'll be able to do a couple things. One of the things that we'll be able to do is connect 2 and 3 together. So here, we can connect 3. We still haven't joined our 2 disconnected pieces of our graph here yet, but we'll be able to do that shortly. Once we go ahead and draw in the graph and put in our 2 here, let's finish up the scratch work over on potential vertices. 2 gets scratched off. I'm trying to make this a different color so you can see where the work goes. 3 still needs to stay underlined because 3 gets used again in the future. But so that's all the things that we can do in terms of scratching off used numbers and everything we can do in drawing the tree. So we're ready to go to step 5. So what should we do for L5? 6. Yep, 6 looks correct. So we're not allowed to use 3 yet, so 6 is the smallest number left in play. And this means now that we're supposed to connect 6 and 3 together. In other words, they're adjacent vertices. And this is actually coincidence, but luckily I put 3 on the correct side here, so we can easily put in the edge 3 to 6, which means we now have a connected graph. You have to have a connected graph in order to be a tree. Okay? So once we go ahead and have this, we've taken care of step 5, except the only thing we haven't done in step 5 is crossed off the numbers that we haven't used. So let's go ahead and cross off 6. Now, last step where we actually have numbers to write down, what should we write down for L6? Yes. So for this one, we should go ahead and write down a 7. It's the smallest number left in play. The only numbers left in play for our choices were 7 and 8. You still weren't allowed to use 3. Okay? Which means that 7 is supposed to be adjacent to 3, so we can go ahead and put that in our graph just fine. And we can go ahead and cross 7 off of our list of potential vertices. Now, At this point, we've exhausted the scratch work in terms of what? In terms of all of these L's to help us build the sequence, help us recover the tree from the sequence. So looking at this tree right here, did we recover all 8 vertices in that tree? And the answer is no. Remember what we ended with on our prufer sequence. We always ended on one last edge that wasn't encoded in the sequence. So we have to put in that last edge. Any guesses how we could read from the information that we have so far, how we could figure out where to attach that last vertex? In this case, the missing one is 3, not 3, 8. Yeah, so the missing edge here is 3, 8, and here's how you spot them. It's the 2 ones that aren't crossed off. Don't overthink it. Exactly. So as one of you said, what's left over? So let me go ahead and put that both in the tree as well as our last step. So last step, remaining 2 vertices are supposed to be adjacent. In our case, oops, didn't put 7. That's embarrassing. 3 and 8. Okay. Now, does this graph look identical to the original graph that we had before? Well, the answer is no, it doesn't look identical, but is it isomorphic? In fact, the only reason, oh no, I think that's a little too small to see. Can you guys actually see that? Maybe with a microphone? Yeah, kind of. Let me go ahead and copy that top graph. We'll put them side to side. All right, copy. We'll put it over here. Boom, paste. Excellent. And now let us get bigger again. All right, so there are the 2 graphs. Notice here they do not look exactly identical, but that's only because we physically put the vertices in a different orientation on the paper. They are in fact still the exact same tree. Notice the 4, 2, 5, 4, 2, 5, that's the same. 2 to 3, 2 to 3, that's the same. The branches here from 3 out to 6, 7, 8, I did them in a slightly different orientation here. So instead of getting a hand wave, I got like a elephant neck type giraffe neck here. So that's a little bit different, and it's rotated sideways. But in terms of the connections, it actually is the same graph. The only difference is it was drawn differently on the page. This one is actually, I mean, you could just say isomorphic, which is true. You could also say equals here as well because it's still legitimately the same graph. Okay? Questions make sense? Kind of feeling a little bit okay. Yes, you could. And actually, the first time I taught this course back a number of summers ago, one of the things that I did is I made very careful to put the vertices, when we were drawing them right here, in this exact same orientation. And in that case, we recovered identically the same graph. But here I didn't bother mainly to show you this thing here where it's okay if the graph doesn't look exactly identical. You really did recover all the same information. Because then, you know, it would freak people out if they didn't get back the exact same picture. So any questions on you guys, on your guys' part? Did this algorithm make sense? All right, I am not seeing any questions on your part. So the next thing that we're going to do is actually an activity on your guys' part. So here's what's going to happen, because it's going to be a little bit different than just a poll everywhere question, although there is a poll everywhere question at the end that I will initiate. And it basically says, are you done with your other activity? Okay. So the poll everywhere question is activated right now. When you're done with the other activity, go in and make a selection. It basically just says, are you done or not? This algorithm only works for trees. So I suppose it could be used to check if 2 trees are isomorphic to each other. So I don't know if people do that much. I haven't heard that. But yeah, I guess it could be. You'd have to do a little bit of adjustments, and you'll see that in this next activity. All right, so directions in terms of the activity. What we're going to use is I'm going to throw you guys into WebEx's breakout sessions. So it has randomized you into 9 different groups as you added today. So I don't see anybody who's added twice, but if you did accidentally add twice, you may be in 2 different groups. So please, hopefully that didn't happen. In terms of the directions that you guys are going to see, actually, let me go ahead and share this window with you guys. I'm going to get rid of the window we just looked at, and you should now see the screen. When you get thrown into your groups, I'm going to send you over to this Zyboard application. So it looks like most of you have 30 out of 40, some of you have joined. As long as at least one of your group members has joined this thing, that person can actually share their screen with everybody else inside of the breakout sessions. So totally fine to do that. Everybody has access to this board, and all of you should be able to write on it at the same time. Please, 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 I can't stress this enough, designate one person or maybe 1 or 2 people in your group to actually write. Otherwise, it'll probably get way too crazy way too quickly. In terms of how to use the board, there are 4 little things here at the top. The first one is drawing. The second one here is erasing. So for example, you can erase like those little dots right there. This one you don't need. It's how I made sticky notes. And if you press on this one that has the arrows, that's the way that you can move around and go somewhere else. So for example, if you're group 1, you'll naturally see this one. And you'll find your group number once you get into the breakout sessions. At the top, it'll say your breakout session number 1, 2, 3, up to 9. But if you're, say, group 4, you'd need to come down here, and they're in a 3x3 setting. Actually, I'll zoom out to show you. So there's 9 of them, 1 through 9. In terms of directions, the directions for what to do is on these little sticky notes right now. There's a 1, 2, 3 step directions. So the first thing to do is it asks you to draw a tree where the prufer sequence is really, really short. The second thing to do is there's at least one other, actually there's exactly 2 other trees from your other classmates, from 2 other groups that are going to be isomorphic to yours. So once you're done, go see if you can find a tree that looks the same as yours. And once you're done with that, let me know that you're actually done by checking out the question right here, which all it asks is, which breakout session did you end up getting in, okay? And that's if somebody comes in after we finish this activity, okay? So that's the plan. Any questions before we go and I throw you into the breakout questions? Circle them. Yep, there are some other tools there too. In terms of drawing, I didn't think that you need anything other than this one, but yeah, there are a bunch of different tools. Down here at the bottom where it says home, that actually pulls you back, and these other ones will zoom in and zoom out as well. Okay, so this one, I'm cautiously optimistic that this will work well in this particular site. Okay, so any questions before I throw you guys into the breakout sessions? All right, so I'm going to talk you through what I'm going to do. In order to throw you guys into these breakout sessions, I do have to stop sharing on my windows, so you may see things go a little haywire on your end. My screens all change when this happens. All right, I'm going to pause our recording because you guys don't need to have anything recorded while this is happening. So the question is whether or not I would ask you if 2 trees were isomorphic to each other or not. Typically, when I ask isomorphic questions, I will normally pick graphs that are not trees, but it is actually fair game if there were 2 trees, you could be asked a question if they were isomorphic or not. Realistically, that's not normally the type of graphs that I choose for those isomorphic questions, but there's nothing that excludes them. Okay. Other questions? I could probably find one. I think I've got some examples somewhere that I could post. Let me write that down and I can get you guys some extra examples. So, extra. I mean, bare minimum. Some of them were the ones that you guys just worked on. But I'll go and see if I can't get a collection of some more. All right. Other questions from you guys? It's definitely easier if you have the tree and then you encode it. Going backwards, it's the same exact technique, but sometimes you have to pay attention a little bit more. It's easy to accidentally connect an edge to the wrong vertex. Okay. So I'm not seeing too many other questions other than you guys just asking whether or not for some more examples. So I can do that. I'll post that later today. And if you notice I forget, just either send me an email or remind me tomorrow. Okay. All right. So in that case, let us, for the rest of today, talk about section 3.2. And one of the things that I will do later on is I will actually take all 9 of those different prufer codes, prufer sequences that you guys had, because everybody had a different one. And I'll actually go through what you should have seen. And looking at your guys' graphs, most of you were spot on. A couple of you guys were a little bit off. And I think maybe 1 or 2 groups didn't totally finish. So I'll go and give you guys the fully worked thing of what it should have looked like. Okay. All right, so moving on to section 3.2. So section 3.2 deals with creating trees from graphs that are not trees. Okay. So first, a little bit of background about why you would care. If you've done anything in a higher level computer related course, you've probably dealt with trees to some extent before. So some of this stuff might be very familiar. If you haven't had those types of courses, this stuff might be brand new. So it could be all sorts of different things here. I typically have about half the people in the course are very comfortable with this topic, and half the people are like, oh, okay, that's what that is. Okay. All right. So first of all, background. Building trees, which are subgraphs of building trees that are subgraphs of another graph, is specifically a way where you can search through that tree, or excuse me, search through that graph in order to get whatever it is you're searching for. Okay. Now, here's when you would decide to actually use a tree as a tool to search through a larger graph. If you need to do something like sequential choices. Okay. The sequential part here, what color am I? Let me not be black. I'm not any color. Okay. Your sequential part in terms of sequential choices, this means that you are following along your edges of the original graph. The choices part, these are us looking at the vertices. So looking at the vertices. Apparently I did not leave myself enough space. So what we're doing here with this notion of sequential choices, this is totally us looking through the internal vertices. And you typically go out to a leaf. But it's mainly going through the internal vertices because that's well, it depends on the graph. But often there's more of them. Again, along some path. Now, do you have to have exactly one path? Not necessarily. Now, dead ends, these guys, when your path ends and you can't go any further and there's no possible way to go any further, this corresponds to leaves of your graph. Okay? So what we do here typically is when you build and we'll define a spanning tree here, the very next thing, but what you typically do is build something called a spanning tree, and this is a subset, not subset, I was dealing with sets earlier today. This is a subgraph of your given graph where you use all the vertices, but you just use some of the edges, enough of the edges so you get a tree, but no extra edges, okay? Which is exactly this definition of a spanning tree. It has to be a tree and contains all of the vertices. One of the ways that you get a spanning tree from the original graph is you keep removing edges until you don't have any more circuits. Because remember, one of the definitions of a tree is you have no circuits. Okay. So suppose we look at this first example. Suppose we look at the cyclograph, and I went ahead and looked at C7 here. I am now regretting that I didn't use the numbers 1 through 7, so it was easy to see that this was C7, but there's 7 vertices here and 7 edges. First thing to note, let me get back to black. Note, what do you guys think? Is C7 a tree? Don't overthink this. Any cycle graph is not a tree with an exception. Anybody spot the exception? Ooh, good call. That is true. C1 would be a tree. C2 would also be a tree. So we typically don't think about cycles in our head or cycle graphs in our head until we get up to 3 vertices and 3 edges, so it looks like a little triangle. So once it's a proper cycle, it actually looks like some polygon, then it's not a tree. But if you have fewer than 3 vertices, 3 edges, you're not going to be a tree. The other thing is we're going to check to see how many different spanning trees there are. So we'll fill in this blank in just a second. It turns out that this particular graph, specifically some cycle, has blank number of spanning trees in it. And we'll fill in that blank in just a second. So let us now go to this cycle graph that we actually have a set number of vertices. We have 7 vertices. Let us find a subgraph that's also a tree. So this is a subgraph. That's a tree. Let's use the technical terms. We want a spanning tree, specifically of C7. Anybody spot one? I'll have to put it right over here, so let me box this note. You got to make sure that you have all of the same vertices. So yeah, the easiest way to actually communicate that is say remove one of the edges. So we have A, B, C, D, E, F. Which edge did you say to remove? DC? All right, so not the bottom one. Yep. So that guy now is what? It's just a length 7 path. And this is something that we did when we were looking at the chromatic polynomials of cycles. We saw that when you removed one of the edges, it turned into a path, which was a tree, which was awesome. But if you contracted one of the edges, it was still just a smaller cycle, and we had to keep iterating through our algorithm. Now, if all you want is a spanning tree, you just remove one edge and you stop. You don't have to keep going like with the chromatic polynomial algorithm. Now, using this example right here of C7, and guess this how many different spanning trees C7 would have. Yep, so there would be 7 different ones. Why would there be 7 different spanning trees for this particular C7 graph? You got it. It doesn't matter which of those edges you use. You could remove any 7 of them, and each of the different 7 edges that you remove would actually give you a different spanning tree. Now, are all those spanning trees isomorphic in this case? Yes, definitely. But they are technically all different spanning trees. Now, extrapolate that out to the general case of any old cycle graph on n vertices where n is 3 or bigger. It's okay to be 3. In that case, it turns out same thing applies. Those cycle graphs in general have n edges. You remove any of those n edges, it will give you a different spanning tree. So that takes care of dealing with this first example. So the next example that we've got here deals with, actually not really an example, it's more of a definition / algorithm of finding a special type of spanning tree. So in this section, there are 2 main special types of spanning trees that your author looks at. And the first one is a depth-first spanning tree. So we're going to look at the pair of spanning trees that are almost always talked about together, depth-first versus breadth-first. Boy, do they sound similar together when you say them out loud. So we're going to start with a depth-first spanning tree, and this talks about how you actually find the spanning tree given an arbitrary graph. Now, the assumption here is that the graph that you're given is not originally a tree. It's some non-tree graph, so you have at least one circuit in the graph. You have at least one subgraph that's one of those cycle graphs. So you start off, you're given any graph G that's not a tree. Then you go and you pick a root. It doesn't matter what vertex you pick. You just determine You pick one of the vertices in the graph and you say, hey, this is my starting point. Just like when we were finding our Hamilton circuits or we were finding any old path or cycle in our graphs previously, you had to pick a starting point. Okay? Doesn't matter which one you pick, any vertex will do. Next, what you do is you're going to build a path specifically from whatever the root is that you picked. So pick a root. Then we're going to build a path specifically from that root, and you want this guy to go as long as possible. So you keep on going. Well, it's maximal as opposed to maximum. You keep on going until you hit a dead end. In other words, you keep going till you can't make the path any longer. It does not have to be the longest path in the graph. It just has to be where you've picked a path and you can't go any further with that particular path. Okay? That dead end is going to turn into a leaf. Okay? Then to pick up the rest of the vertices, because we're trying to build a spanning tree, if you didn't pick up the rest of the vertices without one path, and if you did, it would look something like this guy right here where it is just a path. You then backtrack until you get to the first ancestor of the leaf you just found. So this is your leaf. Okay? And then when you get to the first ancestor of your leaf, so your parent or your grandparent, you keep going back along your path until you get to a branch. In other words, until you get to somebody who's degree 3. Now, why would I say degree 3? Because if you backtrack from your leaf, the parent has to be at least degree 2 because somebody was coming from another vertex to get to the parent and traveling from that parent to get to the child. The only exception to that is if your parent was actually the root. Okay. So then you try to build another path until you reach a dead end, and you keep on repeating those two steps, 2 and 3, until you've reached all your vertices. Okay. So let us do an example of this guy. So for this example right here, make sure I'm on black. We want to find a depth-first spanning tree of this graph G, and this guy was, let me tell you, super fun to draw. So the outside level here looks like a hexagon. You've got 6 vertices, A through F. The inside level right here looks like a triangle. You've got 3 vertices, are G, H, and I. The inside triangle was connected to the outer level in 3 places, every other vertex. And there's also this large triangle that we connected all the vertices that weren't joining the inside and the outside level. Okay? So that's what? A grand total of 9 vertices. Now, if we want to go ahead and build a depth-first spanning tree, the first thing you do is you select the vertex you want. Now, we often select vertex A. So are you guys good with me selecting vertex A? Don't see any fussing about it yet, so I'll mark it. All right, now we're set. So once you're at vertex A, then what you do, you got to pick somewhere to go. Well, if this was me, I'd be really, really lazy, and I'd say, hey, if I want to do a path, maybe I'll do something like where I just go around the outside. Doop, 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 doop. And then we get to F, and we're like, what happens when you get to F? Yeah, you can't go anywhere else. When you get to F here, if we try to go to D, well, that's somebody already in the path. And remember, with paths, you can't repeat vertices. You can't repeat edges. So we can't go back and repeat the vertex D. We can't go and repeat B. We can't go and close it off to A, because what happens in each of those cases, we would be creating a circuit. And what do we not want in a tree? We don't want a circuit in a tree. So if we built this guy, what would happen? We would have started at A, and I always tip my, when I'm building my trees, I always make the edges go a little bit, not straight down, not vertical, but to the side, just because I don't know if there's going to be some branching further on. So then we went to B, then we went to C, then we went to D, then we went to E, and then we went to F. Now, once we're at F, we can't go anywhere, and this is where we backtrack. So if we backtrack, and I'm going to go ahead and pull back up my highlighter, we go back to C. Can we go anywhere from C that's not back to D and not to F? not C, E, E. That was an E. Sorry, E right here. Which is similar to what you wrote in, but you started with C like what I said as opposed to where we actually need to be. So yes, adjusted. So in this particular case here, what can we do? This E, we can come into I, and once we're in at I, we can go to either G or H. It doesn't matter your favorite. Maybe you go to H. Now, then you can only go to G. Why? You can't go back to C because it's been used before. And when we're at G, can we go any further than G in the graph? Remember, you can't revisit vertices you've already done before, you've already visited. This is the key thing with building a tree. You can't close any circuits. So here, right, you can't go any further than G because the only place you could have gone is I, which would have closed a circuit, or A, which is revisiting a vertex we've already visited. Okay? Now, putting this in the actual graph here, the tree that we're building, we went back to E, and then E we went to I, and then I we went to H, and then H we went to G. Now, quick check. With this depth first spanning tree, what did we do? A single path as long as humanly possible with the choices we made. Then we backtracked, and the first place where we could branch off, we branched off and then went on a path as long as humanly possible. Did we actually reach all the vertices in this graph, though? And once you reach all the vertices in your graph, you stop, you're done. Okay? So notice this is almost like, that's not a good example because it would be more applicable to the other type of spanning tree. So I won't say that. Okay? So that would be one way to do a depth first spanning tree. Anybody spot another depth first spanning tree? So notice we went this way, and then here, we went back up, and then down. So anybody spot another one? Ooh, there's one. There's a bunch of different ones, actually, and I see you guys grabbing a bunch of them. A, B, there's one. So suppose you, and let me go ahead and grab a different color here. What's a really obnoxious color? There's a really obnoxious color. Maybe we start at A again, and maybe we do the same thing where we go to B and then to C. But at C, instead of going further on to D, we actually go inside the graph. So here, maybe we go to H, maybe then we go to G, to I, and then at I you're forced. You have to go back out to E. Now at E, notice what you can do. You can go to either F or D. It doesn't matter which. Maybe you go on to F. And notice at F, the only option you have is to come back to D. Now, whoa, getting back to black. With this guy, that is one single path. With that one single path, did we actually visit all the vertices? And while you guys are checking that, I'm going to write it out what we just did. So did we visit all the vertices? Because if not, we got to go find the ones we missed. Yeah, we totally did. So this guy is another option of a depth first spanning tree. And as one of you said, but I think it wasn't to everybody, if you are able to find a Hamilton path, in other words, a path that actually visits all of the different vertices, that is always going to be a depth first spanning tree. You know, always be a depth first spanning tree that's isomorphic to just a single path. Okay? Both of these are completely legitimate depth first spanning trees for that particular graph. Notice this one had the maximum length path because it was one single path that reached all of your vertices. This one here first got a maximal path because you got to a dead end, you couldn't go any further, but it actually wasn't the longest path in the graph itself. Okay? So that's the difference between these two guys, but both of them are depth first spanning trees. Okay? Make sense? Feeling comfortable? Questions so far? All right, I'm not seeing any questions come in, so let us look at the other type of graph, and this guy is the breadth first spanning tree. And it all depends on what you need of which one of these guys you use. Okay. So for your breadth first spanning tree, and let me blow this up a little bit here. This one starts off the exact same way as the depth first spanning tree. Specifically, you start off with some graph. You don't take a graph that's also a tree because the whole point of getting this spanning tree is to build a tree, okay? You then pick a root. Doesn't matter which vertex you pick as the root. Maybe you're told, maybe you're not told. So you go and you pick whatever vertex you want to be your root based on whatever criteria or no criteria that you have. Now, here's where everything changes. At step 2, what you do is you select all the vertices that are adjacent to your root, and you're going to put them in the first level of the rooted tree you're building. Please note both the depth first and the breadth first spanning tree that you built are technically rooted trees. Do we put in the little arrows? Personal preference, you could, but often you don't. So the thing in terms of the root, it's really just mainly your starting point, if you will. A lot of people, when they find these spanning trees, actually will just highlight the edges in the graph themselves. And if they do it that way, you don't have any really indicator of who that root was. It's literally just a starting point of how to travel through the graph. All right, so breadth first, we selected all the vertices adjacent to the root, placed them in level 1 of your tree. So as you're thinking about this, you've got here whoever your root was, and let me make that a different color. So here's your root. Everybody adjacent to your root gets right here. However many of them there are. Okay. Now, each one of these vertices, so maybe this is vertex A, what you do is you then look at all the vertices adjacent to vertex A, and you include them down at level 2. Now, here's the caveat. You are actually trying to build a tree. So if the vertices that are adjacent to A are already in your graph, don't put in an edge like this across to that same level. That is not a valid edge, okay? So you're only picking the new vertices that haven't already been included on the same or higher up levels. You shouldn't really have too many higher up levels. I guess technically the root there, okay? And then you continuously do this. Standards are to travel left to right in terms of looking at each level, but you don't have to do that. If you travel right to left, your breadth first spanning tree can actually look different because it'll depend on if 2 vertices on the same level are adjacent to a common third vertex. Okay. So just like with the depth first search spanning tree, you can also have different outcomes with the breadth first spanning tree. So let us look at an example, and for as long as possible, we'll keep the directions up there at the top. On purpose, I chose the exact same graph that we had before, mainly so you could see how different the depth first versus breadth first spanning trees look. All of these guys that we're building are spanning trees. They just different ways that we got them. Okay. Now, to really try to hone in on the differences between your breadth first and depth first spanning trees, I'm going to on purpose pick the same starting point. So if you guys had picked a different root earlier, we would have stayed with whatever that vertex was, but we went ahead and we went with A. So I'm going to keep the root here at A. Okay. Now, if we want to go ahead and build this, I didn't change out the word here. Breadth first spanning tree. First thing you do with your graph is you pick your root. We did that. So we'll put our root right over here. Next thing we do is we look at all the vertices adjacent to your root. Now, in our particular case, who is adjacent to A? You got it. So it's got 3 guys adjacent to A. I normally put them in alphabetical order, but you don't have to. I see several of you guys put them in the exact same order that you would have read them in the graph right here. So I'll mimic what you guys sent me. So F, G, and B, and you go ahead and you connect in. Now, some people like to go ahead and as they're building this spanning tree, we go and highlight the edges in the graph itself. I'll be honest, I don't normally do that with a breadth first spanning tree. I do it normally with a depth first, but it doesn't matter. You can totally do it in either case. Now, what would be the advantage of highlighting these edges? Don't close a circuit. And it's much easier to see if you're not closing a circuit. I shouldn't say it that way because it's easy to see over here too. Sometimes people get clued in that they're closing a circuit easier in the original graph. Don't know why, but I have seen that in work time and time again. So if we start here, and you have to pick these three vertices to start with. It doesn't matter which one we start with. So which of these three vertices would you guys like us to focus on next? Sure. So if we start at F, F is currently a degree 4 vertex. I lost my cursor. Degree 4 vertex right here. Don't include the edge F to A because it's already in the tree. But it is right here adjacent to B. Don't include B. Why? Because that would close the circuit. So the only new two vertices that we're adjacent to are D and E. So we'll put D and E down here. Okay. So let me highlight those two since we highlighted edges previously. Now, once you deal with F, don't keep going. That would that would merge the two techniques together. Instead, deal with every vertex on a single level before you go any further. So the key thing here is the depth first search is super, super tall. The height is as tall as possible. The breadth first search, the height of your rooted tree is going to be as short as possible. Okay? So do you guys want to focus in on vertex B or G next? It doesn't matter. G, all right. So if we look at G next, we'll look here at our graph G, and we say, all right, well, who's an edge that's incident to G that we haven't used yet? Well, we could go out to H, or we could go out to I. Is there any problem of including the edge that goes to J or the edge that goes to H or the edge that goes to I in the graph? In other words, if we add in the vertices H and I here, are there any issues? Yes, it would. So in this particular case here, if we looked at G first before B or B first before G, it would in fact be a different tree. They'll actually be mirror images of each other. And just a second, I'll actually show you the original one that I had prepped up before class, which looks different than this one too. So let's go ahead and finish off G like we had talked about, and then we'll grab B. So we grab both H and I like you guys said. So here's H, here's I. That was trying to be an I. And if we then go down to B, which is the only one left, we can't include D, we can only include C. That's the only new one. It turns out with this particular one, since so many of these guys are degree 4 or degree 3 at this level, depending on which one you start with, which one you end with, one of them will have one child and the other two will have 2 children. So for example, if we'd done B first here, B would still have had the child C, but B would also have had the child D as well, and then F would not have had the child D. So you'll still get the same vertices here at the same level. That's not always true as well, depending on how the edges are. In this graph, these vertices would still be at level 2, but they would be connected up as the children to different guys if you actually walked through this graph in a different order. You guys want me to show you the other option? I've got space. So we could do something like this, or. So this is actually the way that I originally did it. A, and I actually ordered B first, then F, and then G. I just default to alphabetical. So then if we looked at B first, we just said this, B would connect to C and D. Notice it picked up an extra child. If we then looked at F, F is only connecting to E because D was picked up as a child of D. And G is actually still connected to both H and I. So this one is isomorphic, but the connections are a little different. And they're not always isomorphic. We saw with the depth first search, we didn't get even isomorphic trees. This one, we actually got isomorphic trees. If you actually wanted to get somebody who's not isomorphic, you could actually change up your root. Maybe you changed your root to be F, and in that case, the degree of your root would be 4, and we'd have 4 little guys on level 1 here. So let me write some of those comments down. And let me put a different color so it's easy to spot. So comment. Your height, and this we said a little bit ago, of the breadth first spanning tree is always less than or equal to the height of the depth first. And here's a fun fact. See if you guys can answer this one. If graph G is disconnected, any guesses what happens in terms of these spanning trees? If your graph is disconnected, do we have a spanning tree? Ooh, good call. There's not a single spanning tree, so no spanning tree, but you could have a spanning tree on each component. So I guess the way that you would say this is, I don't think this is actually a term, a spanning forest. So on each end, I have never heard that term before, but I would vote for that term for this thing. Sorry, focusing. You would have a spanning tree on each one of the connected components of your disconnecting graph, but not a single spanning tree, which is typically what, in this connotation, if people say, hey, do you have a spanning tree on your disconnected graph? The answer would be no, and then the follow-up would be, hey, wait, but I could totally do a spanning tree on each of the components. Now, the next example that I've got prepped up for us is one that is going to take, definitely longer than our 3 minutes remaining. So do you guys have any questions about the depth first or the breadth first trees? Or I should say spanning trees, excuse me. Any questions so far about what we talked about? All right. Well, in that case, I'm going to end us early today. I'll end this right here just because this is a good stopping point. Next time, we'll have only 2 things. What was the first again? Which one? Oh, it's the word first, breadth first. That's all it was. I just abbreviated because I was going, I thought I'd be able to get to the next example and we weren't. Okay. So that's all it is. It was just my shorthand. That's it. In terms of things that we'll do next time, the next example that we have is actually it's actually going to be a proof question. It's going to be, hey, there's this fact, and here's why it's true. And then the last thing that we're going to look at is what are known as pre-order and post-order, and it is another way to encode trees. So like prufer sequences was a way to encode trees. This will now be another way to encode trees, and that'll be it in section 3.2. So we'll definitely start and probably get about halfway through section 3.3 as well tomorrow, and so we'll probably finish up chapter 3 on Friday is the current plan. That being said, your homework for section 3.2, I went ahead and called it last night and moved it to Monday, so you don't have that. You've just got the homework for section 3.4 and 3.1 due on Thursday. Also, if you didn't have a chance to do it, because it looks like we're missing 1 or 2 people, if you didn't log in and tag yourself of which group you were in the breakout sessions for this time, do please let me know, because I'm going to follow up and send you guys personalized information about what you did, okay? So if you would do that for me as well. But I'll go ahead and hang out for a little bit if anybody's got questions, but otherwise, that is it for today. We are done.